Okay, this is AQA, A-Level Physics, 2024, paper 2. As per usual, can't show the paper on screen, otherwise AQA will get the whole channel cancelled, like they almost did in the past. So link to paper and the mark schema in the description. 1.1, we have air at a temperature of 20 degrees. We know we're going to have to turn that into Kelvin, so we might as well do that now. So temperature is equal to that 20 degrees plus 273. Just get shifted. So that gives us 293 Kelvin. And a pressure of 105 kilopascals. I'm going to say 1.05 times 10 to the 5 pascals. So the amount of air in each cubic meter is about 40 moles. So we're looking for, in each cubic meter, we're looking for number of moles, that's N, divided by volume. That's what we're looking for. That would be moles per meter cubed. So let's have a look at our equation. We have PV equals big N KT. In this case, we're going to go for N RT. So therefore, rearranging this for N over V, we end up with P over RT. So that's 1.05 times 10 to the 5 divided by our gas constant of 8.31, molar gas constant that is, and then multiply that by 293. Sure enough, that gives us 43 moles. We can say per meter cubed if we wanted to. 1.2, density is 1.25 kilograms per meter cubed. Calculate CRMS. Okay, so we're going to need our data from over here again. So quite often I often think that the equation for density is in the formula sheet, but it's not actually, so we need to derive it. So density is equal to mass divided by volume. But the thing is that we're talking about total mass, and so that has to be the number of particles times the mass of each molecule divided by the volume. So we are going to need our other equation. So PV equals, this is in the formula sheet, which is good. So a third NM CRMS squared. So therefore we can see that we have NM and V in there. So we're going to pop V over here. And so we can say therefore pressure is equal to a third times the density times, I'm just going to say C squared there. So therefore, C is equal to, rearranging this, or let's say C squared first, is equal to 3P, taking a third over the other side, divided by the density. So therefore, C is just going to be the square root of all of that. Don't get your rho and P mixed up. Therefore, C is equal to the square root of 3 times, what was the pressure? There we go, 1.05 times 10 to the 5 divided by our density. And we end up with 502 meters per second. Nice start. But yeah, get used to knowing how to get NM over V for density. Very, very useful, quite common, comes up a lot. Okay, what will be the temperature that will double CRMS for the air molecules? Okay, well, that's easy. It's just proportionality. So we know that energy is equal to 3/2 kT, and energy is, half mc RMS squared. And so therefore, we can just say that C squared is proportional to T. So therefore, if we want C to double, that means that C squared goes up by a factor of 4. So that means so must the temperature. Therefore, new temperature is equal to, what was it? 293 times by 4. And that gives us 1172 Kelvin. And yeah, they caught me out. I would have given that as the answer. Only would have got a 1 mark for that. Why? Because they're looking for the change in temperature. Therefore, delta T is going to be this. Take away that. And so I could have just done 3 times 293 instead, but there we go. 2 ways of doing that. So the temperature difference is that many Kelvin. 1.4, oh man, loads of flipping information here. A room contains moist air. Okay, temperature of, well, okay, so temperature is 293 again, Kelvin. Dehumidifier cools, condenses water vapor and moist air. The final temperature of the liquid water that collects in the dehumidifier is 10 degrees. Okay. Oh, okay. This is This is not gases, so we don't actually need that. We don't need Kelvin, because when it comes to specific heat capacity, we only care about a change in temperature. So actually we can just leave that as 20 degrees for now. You know, there's no point converting it to, oh man, this looks complicated. So we've got the moist air flowing in. I'm so confused about this. Mass of water divided by the mass of air. What on earth? Moist in... Dry out. I think this is probably one of the questions I would have left until last if I was doing the exam proper. In 1 hour, okay, so time is 3,600 seconds. Volume of 960 meters cubed, right? Assuming the density again remains at that. Okay, determine how much energy is removed in 1 hour. Okay, fine. So, the energy out, or the energy, the total change in energy is going to be the energy to cool plus the energy to condense. Okay, let's have a think about this. This is the energy to cool the water, and it's the energy to condense the water vapor into water. So we don't care about the air, I guess. Right, so therefore, the mass of water, oh my days, this is what's confusing me. So the mass of water divided by the mass of the air, the difference in those is going to be that 0.0057, take away that, one take away the other, so it's going to be 0.002. Ultimately, we want this, so can we find the mass of the air? Yes, we can, because we have the density and the volume. This is not an easy one to wrap your head around. Okay, so the mass of the air is going to be equal to rho v. So there's going to be 1.25 times by 960. So it's 1,200 kilograms. That seems like a lot. Okay, it's an hour. Whatever. And so therefore, if we pop this, if we pop this in here, we can say the mass of the water is equal to 0.002. This is what is, they didn't need to add this part. That's the stupid thing about this. 0.2. I could have done this in my head, but whatever. That gives us 2.4 kilograms of water cooled and condensed. Right, so now we have that. Cool. So now we can do this. So delta E is going to be equal to the energy needed to cool the water vapor, that is. Okay, so that's going to be mc delta theta, delta t, whatever. I'm going to use delta t, plus ml. Okay, that's that. That is that. And so that's going to be, can I factorize that? So that's 1,860 times by, what was the temperature difference? It's going from 20 to 10 degrees. Okay, plus the latent heat of vaporization, 2.3 times 10 to the 6. Okay, we're just going to work out. So I end up with 5.6 times 10 to the 6 joules. So this is the thing. This is two questions in one, really. So yeah, this is what confusing me, because we're not talking about reaching 100 degrees, are we? We're not boiling. We just happen to be condensing. I mean, you know, that's what happens when you pressurize it. Okay, so yeah, so all of the water that goes in the water vapor is condensed. So it is cooled by 10 degrees and it's condensed as well. So that's how we came up with this equation here. Capacitors, we have this circuit, that's our capacitor C. We have a switch and a resistor. PD is across the resistor. That's something that we need to bear in mind. It's not across the capacitor. Oh, we got two of them, right? We got one across each. Okay, the switch is closed. The PD across C is recorded. Fine. Explain how the gradients of the graph can be used to determine the initial current I0 in the graph. Okay, easy peasy. So let's have a look at what the gradient actually is first of all. So we have gradient is equal to, it's going to be change in voltage over change in time. You know, don't worry about the deltas too much. And what do we know current to be? Current is equal to charge divided by time. And so how do we get from here to here? We have V divided by time, Q divided by time. So therefore, we're going to have to use our capacitance. It's a little bit annoying that the question doesn't say how do you, it implies that it's just the gradient that you use. But no, we need to know the capacitance as well. Q equals VC or CV. So therefore, I'm going to replace V with Q over C. Pop this into there. Therefore, gradient is equal to Q over C over T, or in other words, Q over CT. So therefore, as we can see, this and this are the same. Therefore, gradient is equal to the current divided by the capacitance. Therefore, current is equal to gradient times the capacitance. Weird question. Oh, by the way, I should have said it was the initial gradient, of course, because that's what we want. We want the initial current, because of course we can see the current is slowing down, as we know what happens with a capacitor when it charges. Okay, we have a graph of V against T, classic exponential decay graph. Okay, shows the difference between 20 and 45 seconds. Doesn't matter too much, you know, because we're just talking about the time from when we start. The capacitance is 31 microfarads. So I'm going to say that, or 3.1 times 10 to the minus 5. Okay, using the time constant, go on to show the resistance of R is about 2.5. So we're looking for the resistance. Easy, easy peasy, guys. So easy. It's a 1 mark question if you ask me. Time constant, TC, that gives you, if you use a good number to remember, 0.37 or 37% of an initial value. Why is that? Well, if you remember, when it comes to this, with time constant, when T is RC, V over V0 is equal to E to the minus 1, and that gives us 0.37. So this ratio of an initial value, could be voltage, it could be charge, it could be current, is going to be 0.37. So that's all we need to say. So let's get 37% of an initial value. So we're going to go 0.6. Yeah, let's go 0.62. So V0 equals 0.62 volts. And therefore, 0.62 times 0.37 gives us 0.2. Let's just go with 0.23 volts. Okay, so reading off the graph, it looks like it's bang on 27.5 seconds. Therefore, RC, the time constant, is going to be equal to 20 to 27.5, so that's just 7.5 seconds. Therefore, finally, we just want the resistance. Resistance is equal to the time constant divided by the capacitance, so that's 7.5. divided by our capacitance of 3.1 times 10 to the minus 5. And that gives us 2.4 times 10 to the 5 ohms. Is that what we were looking for? Yeah, happy days. So yes, as soon as you have a graph of capacitor decay, then all you have to do is find the time constant. Much like 37%, much like when it comes to radioactivity, when you have a graph of that decay, you're always looking for the half-life. But this is the 37% life. 2.3, current at time 0 is 3.6 times 10 to the minus 5 amps. Determine the time at which VC is 6 volts. Okay, T equals something for VC equals 6 volts. So what, are we going back in time? No, what? Right, so this is a bit tricky because we don't know the EMF. We don't know the voltage supplied. And that's what we need to find out first. What is the PD of the battery? Because then we can just take away one PD away from the other with regards to the capacitor and resistor. Okay, so they've given us I0. So therefore, right, at the beginning, when you start charging at time 0, the only thing that's, you know, I mean, the only PD is across the resistor. There's 0 PD across the capacitor. And we can see that from the graph earlier, can't we? So we can just say that V equals IR. So V equals I0R. Cool. So we found that earlier. We found the resistance earlier. And so that's 3.6 times 10 to the minus 5 times by, what was it? Whoops, it's right there. 2.4. times 10 to the 5. That's nice. They cancel each other out. So that is 8.64 volts. So that's our initial PD. Marvelous. We're looking for the time when VC is 6 volts. Cool. So we can just use our normal equation, V over V0. I always like writing it out this way because it's just clear then that it's a ratio that we're dealing with. But in this case, yes, okay, we can rearrange it. That's fine. So minus T over RC. Now, I just realized I haven't properly thought carefully about what's going on here. Look, when we look at the graph above of this decay, this is V that's falling across the resistor. We are actually charging the capacitor, aren't we? So we can't just use this as is, no, because we're dealing with the opposite voltage. We're dealing with the opposite PD. So therefore, we're going to have to say that it's the whole, not this, but rather it's the 1 minus version. So not this, but we're going for V over V0 is equal to 1 minus e to the minus t over RC. Right, there we go. So we're going to say, I'm just rearranging it. I'm just going to swap V over V0 with e to the minus t over RC. So we end up with this. And so therefore, the log, natural log of that is equal to minus t over RC. And so therefore, the time is going to be equal to just minus RC times by the log of 1 minus V over V0. And so that is equal to, we already have our time constant actually from above, so we can just say 7.5 times log of 1 minus 6 over 8.64. And that gives us 8.9 seconds. That is not an easy question. As per usual, questions that involve the looking at charging are way harder than questions that involve discharging, because you have to think really carefully. And also we have the added layer of complexity with the resistor instead that we're looking at the PD across the resistor. You just got to think, right, are we charging or discharging? I honestly, I saw the decay graph and I immediately went into discharge mode, but you've got to remember that that is for the resistor in this case. And so therefore this is a charging question. And so just be very wary of that. Whenever you see a charging capacitor question, you're probably most likely going to have to be using this version of the equation instead. Okay, so essentially we have that, right? Okay, so this is V1, this is V2, this is C1, C2, right. Okay, so we're given some values for charge, surface area, etc. Okay, that's okay. That's good actually, because they've told us about charge being the same. That's good. So we're looking for V over V1 over V2. Right. So let's get our capacitance equation for dielectric and all that jazz. I've probably written that the wrong way around, but it doesn't matter too much. So therefore, we can see that for what's different. Okay, plate separation and dielectric constant. Okay, so therefore we can say that C is proportional to, surface area is the same, so that's staying the same, that obviously stays the same. So therefore we're going to say that C, capacitance, is proportional to epsilon R over D. Okay, and what are we looking for? We're looking for V1 over V2. Now, as per usual, when it comes to questions that ask you to find a ratio of two things that are the same, so no unit, we want to replace them with what they're proportional to. So we have here C is proportional to epsilon. I'm just going to call that epsilon. We don't need to call it epsilon R. So therefore, we know we're going to have to use our just normal capacitance equation. So we can see that Q is equal to VC. So therefore, V is equal to Q over C. Now, Q is the same for both, as we can see from the table. So therefore, we can say that V is proportional to 1 over C. It's inversely proportional to the capacitance. So therefore, we can replace, you can do this in a couple of ways, but I'm going to do it this way. We're going to pop that in there instead. So therefore, we can see that V is proportional to 1 over epsilon over D, or in other words, it's proportional to D over epsilon. So I'm going to say V1 over V2 is equal to, again, we replace it then with what they're proportional. So that's D 1 over epsilon 1 over D2 over epsilon 2. We want to combine these ratios into, or separate the ratios rather. So we end up with D1 over D2. This epsilon 2 ends up on top. So it ends up being epsilon 2 over epsilon 1. Okay, D1 over D2. This ends up being, what's that? A half, yep. It's 1 over 2, and then that's going to be 1 over 4. So it ends up being an eighth, or in other words, 0.125. Not a super easy question, though. Okay, 3.1, we have the flux density of the Earth's magnetic field is 4.9 times 10 to the minus 5 Tesla. And we have an angle, okay, so we have an angle of 68 degrees. Now we've got to be careful. Are we going to use that or sine or cos? We'll talk about that in a second, I guess. And we have a rod that is falling to the ground, 8 meters. Okay, determine the average EMF across the rod during its fall to the ground. Okay, so EMF is equal to rate of change of flux. But we can derive this, but it's a useful... Is it in your formula sheet, actually? I don't know. Oh, I forgot the length. Length is 2 meters. I don't think BLV is in your formula sheet. That's a good equation to remember, guys. Okay. Yeah, it's not there. Interesting. Well, if you want to know how to derive it real quick, it's in my video anyway, but here we go. EMF is equal to rate of change of flux. And we know that, I'm going to drop the deltas. We know that flux is equal to flux density times area divided by time. And area is equal to length times distance. We're going to say BLD divided by T. And of course, D over T ends up being V. So that's where we get our equation from. But this is when they are perpendicular. That's the thing. So when they're perpendicular. Here's the issue is that it's not falling perpendicular. It's falling at an angle. It would be BLV if the magnetic field was horizontal like that. It's not. We are turning away from the horizontal with our 68 degrees. So therefore, it's going to be BLV cos 68. There we go. So hopefully that gives us the answer. So 4.9 times 10 to the minus 5 times by 2 times by... Oh, okay. How do we find average V? Right. Well, that's okay because we can just use SUVAT for that, can't we? We want the final velocity and then we'll do... Yeah, there we go. So that 8 meters... we want final V and A is 9.8. So V squared equals U squared plus 2AS. That goes. So therefore V is equal to the square root of 2AS. So that's equal to square root of 2 times 9.8 times 8. I thought there might have been an extra step here. And that gives us 12.52. So therefore average V is going to be half that. So let's just say 6.26 meters per second. So there we go, popping that in here then, times by cos 68. Okay, let's cross our fingers, guys. And that gives us 2.3 times 10 to the minus 4. We're looking at volts, of course, it's an EMF. So there we go. They like these kind of questions these days where they're looking for an average speed on average, and you just have to go, well, here's the beginning value, here's the end value. We just want halfway in between. We've seen that in a couple of years' papers now. Not a super easy question, but quite nice. Okay, what on earth is going on now? The rod is returned to its original position. It's now supported by a non-conducting pole. During each fall, there are... What? Who came up with this? There are changes in the magnitude and direction of the induced EMF. These changes differ depending on whether or not the rod falls to the left or the right. Yes, we can see that. Explain why changes in the magnitude and direction of the... Okay. What? Explain any changes in the magnitude and direction. Right. Okay. That's easy. So, to the left, we can say that angle to B decreases. It even decreases to 0 at around midpoint because it's falling in line with the magnetic field line. So 0 around midpoint. Therefore, and then decreases again, and then increases again before hitting ground. Therefore, small EMF induced, then it goes to 0, then reverses. So the opposite EMF is induced. Okay, and then what about to the right? Well, we can see that it's cutting the field lines a lot more. To right, angle increases to 90 degrees, then decreases before hitting the ground. Therefore, max EMF induced when at 90 degrees to field, then decreases again, but it doesn't reverse. Well, there we go. Weird question, that one. Kind of all right there. 4.1, one purpose of the coolant is to maintain a safe working temperature. State the other purpose is to transfer mean, that's not really a point of it. The point is to take heat away to be used. That's ridiculous. So transfer heat to boiler to create steam, which turns the turbine, blah, 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 blah. Of course, it isn't the coolant that gets turned into, from water. It's not the coolant that gets turned into steam. It just goes into a heat transfer device, so it's a boiler. 4.2, two properties that engineers consider when choosing a liquid. It must have a high SHC. And that's the case for any coolant because you want it to absorb, or you want it to take in a lot of energy before the temperature increases. So that means energy gets taken away a lot more quickly. It's more efficient. What's the other thing we could say? You could talk about thermal conductivity, but that's kind of the same thing as SHC. Not quite, but they're sort of the same thing, so I'm not going to put that again. What's another good thing we can say? It must have a high boiling point because we don't want it. We want it to stay as a liquid because if it turns into a gas, then things will not work as well. How is the power output decreased? Control rods, of course. There's no off switch. Control rods are... and there's a very important point coming up, inserted more or further between fuel rods. These absorb neutrons without, and this is the really important bit that you always have to put, without further fission induced. That's the point, because fuel rods absorb neutrons as well, don't they? But of course that results in fission. We want them to be absorbed with no fission taking place. Okay, 5.1, we have this Earth and we have a moon, the moon rather. I'm not an alien, guys, I swear. And it looks like the moon is going along an equipotential. Let me pop that in blue there. And then we have another equipotential over here. So I think we're going to be looking at potential and, I don't know, energy and that kind of thing. So, what are we being asked? Resultant force on S1 is due to the gravitational forces from the... Oh, sorry, S1 is a... What is it? Oh, it's a satellite. Whoops. Well, draw a satellite then, guys. Don't do a little spot. Resultant force on S1 is due to the gravitational forces from the Earth and the Moon. Fine. Okay, so it's always behind the Moon. That's weird. The magnitude of the Earth's gravitational field... Okay. So we have two gravitational fields. Show that GM is approximately that. Right. Okay. So, oh gosh. So total G for the satellite is equal to G due to the Earth plus G due to the Moon. And so we're looking for this, aren't we? So therefore GM is equal to G. I'm just going to call it G. Take away G of the Earth. Fine. So the question is how do we find this gravitational field strength, this total gravitational field strength? Well, as per usual with satellites, the first thing we write down is GM over R squared. That's the force due to gravity. And that is going to be equal to, that's the total, even though, yeah, we'll get onto that in a sec. And that is equal to, well, either mv squared over R or m omega squared R, but we're given the period of the moon's orbit, so therefore we're going to say omega squared R. We're going to have our angular speed in there instead. Okay, one of the m's cancels, and of course you should notice that gm over r squared, that is our gravitational field strength, so therefore g is equal to omega squared r. Cool, so all we have to do then is say g is equal to, well, we can replace that with, of course, 2 pi f squared r, or 2 pi over t squared r. Let's go for that, there we go. But I'm going to say that that is 4 pi squared r over t squared. Cool. So that's our g. So let's pop that in. So that's 4 pi squared times by the radius. 4.489 times 10 to the 5 kilometers. So that's times 10 to the 8 meters then. Divided by the time period. And that is 23.7 days. So we need to do 27.3 times by 24 times by 3,600. And that is all squared. Woo, lads. Let's have a look and see if this ends up being correct. That gives me 0.0, well, let's write a standard form. 3.19 times 10 to the minus 3, and the unit, of course, is newtons per kilogram. Seems very small, but I guess it is far, far out, man. Okay, so therefore GM is just going to be this, take away, the other one's really small as well, fine. The gravitational field strength due to the Earth, that wasn't a good 3. So can I do that in my head? Yes, I think I can. That's going to be 1.21 times 10 to the minus 3 newtons per kilogram. Okay, 5.2, calculate the distance. Okay, distance between the satellite and the moon. Okay, we're given the mass of the moon. And, well, what else do we know about the moon? Well, we know we've just calculated its gravitational field strength for the satellite, so that's okay. So we're going to say G is equal to 1.21 times 10 to the minus 3. And we're looking for distance. So therefore, do we have an equation that links all these? Yes, we do. Like we just saw, gravitational field strength is equal to this. And so therefore, R is equal to the square root of G over G. So that's the square root of 6.67 times 10 to the minus 11 times the mass of the moon. And I'm going to tidy up some powers of 10, so times by 22, that just ends up being 11, divided by G, and that is 1.21 times 10 to the minus 3. I tell you what, I'm going to add 3 onto the top there. So this just ends up being times 10 to the 14. And that gives me 6.37 times 10 to the 7 meters. There we go. Not an easy question, though. Ah, yes, if there's an S1, you can bet your bottom dollar there's going to be an S2. Here's the second satellite that's now in front of the moon. So what do we do here? Explain how the resultant force on S2 due to the gravitational fields of the moon causes S2 to orbit with the same angular speed of the moon. No calculations are required. Interesting. Okay, so now G total, or G is equal to G E minus GM. Therefore, gravitational field strength is less. But as distance to Earth is smaller, GE is larger for S2. Therefore, G is same for both S1 and S2. Therefore, same angular velocity. Period. Weird question. Mark Scheme says it in a weird way. I don't know. Okay, 6.1. Electric potential at a point in an electric field is minus 4 volts. What is meant by this statement? Okay, so potential is equal to potential energy divided by charge. We know that just from voltage, don't we? So that means that therefore, if it's minus 4 volts, that means that, well, what is potential for starters? So potential, the definition is, potential is the work required to move unit charge, and so that means per coulomb, in this case anyway, with electric fields, per unit charge from infinity to that point. I know it seems like it's the wrong way around, but that's why it's a minus. Therefore, V equals 4 volts or minus 4 volts, 4 joules of work required to move 1 coulomb of charge from that point to infinity. What is going on here now in figure 9? What do we have? Confined groups of electrons and electrodes. Okay. Gallium arsenide. Sounds a bit scary. Electrons can only move along line PQ. Electrons can only... Okay, so they can oscillate. Fine. Wait, can they oscillate? Oh, I don't know. Electrons can only move... Okay. When a suitable electric potential is applied to the electrodes are confined. Oh, they are confined. Right. Determine using the graph the maximum magnitude... A lot of flipping fluff. They're setting up this question. The maximum magnitude of the electric field. State inappropriate. Okay, right. So we have V against X here. So we know that electric field strength is equal to... Well, the unit is newtons per coulomb, if you can... not remember the equation, so therefore that means that it's well, if you see my video on fields, I think it's a good way of looking at things. So Q1, Q2 for force over there, and then we go over to here, which gives us potential energy, so EP. I always do that accidentally. I go straight for gravitational fields, and then potential is equal to KQ over R, and then electric field strength is equal to KQ over R squared. Okay, so we have a graph for potential. We need to get to electric field strength. And as you can see, we are dividing by R. And so that means that, well, if you remember, field strength is also known as potential gradient. Therefore, E is equal to delta V over delta R, or in this case, delta V over delta X. So therefore, it's the gradient of the graph. And so therefore, we want the max gradient. All we have to do is just with the steep bits of the graph, and we should end up with something like 2 times 10 to the 7 newtons per coulomb. And of course the unit, is newtons per coulomb, isn't it? So 6.3, an electron at rest, 300 mil, gains kinetic energy and moves to 800 mil. Sorry, nanometers. My eyes don't work like they used to. Okay, determine the minimum kinetic energy required by the electron. All right, so we're just talking about the change in, so Ke is equal to the change in potential energy, easy peasy. And so therefore we can say from 300 to 800 nanometers, it's just peak to peak. Right, I see. So that's a little bit cheeky because, it's going from peak to peak, but it has to have enough kinetic energy to go to the bottom there to begin with. So actually we're just talking about going from delta V is equal to, so that's 0.2 minus 0.2 whatever to 3.4. Yeah, 3.4. So therefore that's equal to 3.2 volts. Is that right? Okay. And then we know that energy or change of potential or work done rather is equal to QV or Q delta V. And we can see that from our graph up here to go from one to the other. From potential to that, we multiply by a charge. And so therefore, all we need to do to get from one to the other is just multiply by that, of course. So therefore, work done or change of potential energy, same thing, is equals to Q delta V. So that's, it's an electron, so it's 1.6 times 10 to the minus 19 times by 3.2. And that gives us 5.12 times 10 to the minus 19 joules. 6.4, one of the confined electrons is at 350 nanometers. This is a weird question. So let's have a look at the graph. So 350 nanometers. Okay, whatever. Discuss the subsequent motion of this electron due to the variation in electric potential shown in figure 9. Assuming the electron starts from rest. Right. Okay, so they want to get to a lower volt potential, rather. So they want to go down. And so that means that if it's at 350 nanometers, then it will go to the right. No, of course not. Right, let's have a think about this. Look. Electric fields are all relative to positive charges, or they affect positive charges. That's what we think about. Therefore, if a proton would move to a lower potential, and so that would be to the right. So if you think about it, so at, say, 550 nanometers, there would be a negative charge there pulling the proton along. But as it's a proton, as it's an electron, would move in opposite direction. It would move to the left. And then it would stop at 300. Unless it maybe it wouldn't stop actually. So it probably wouldn't stop, but it would actually oscillate around 300 nanometers. That's where we have a Vmax. It's not going to stop dead. It's got, do you know what? I should probably put something about kinetic energy. Fine. Well, actually, we don't know. Yeah, no, it would have some kinetic energy. So we're going to say the loss in potential energy. So we're going to say loss in PE between 350 nanometers to 300 nanometers. So it's whipping towards 300 equals gain in KE, therefore would overshoot. And that's why it oscillates. So this is ultimately just oscillations that's going on. But yeah, weird question. Question 7, radioactive dice. We have an actual log graph, log axes. Explain why n has been plotted on a logarithmic scale. Well, it's because allows for accurate reading, plotting and reading over multiple orders of magnitude. Because you could plot it just normally without, but of course it would go down like that really, really quick, and then it would go like that for ages because it's so small. But by doing a log graph, we mitigate that. Okay, 7.2. In this experiment, decay constant can be defined. Okay, fine. So it's just like radioactive decay. Go on to use your value. Oh, determine lambda. Okay, so lambda, we know that half-life is equal to log 2 over lambda, or vice versa. And so therefore, lambda is equal to log 2 over the half-life. So this is equal to log 2 divided by, right, what's the half-life? We're going to have to read off this graph. Oh, that's not too bad. So we're going from, oh, it's not 1,000, it's 900. Yeah, 100, 200, 300, 400, 500, 700, 800. Okay, yeah, so it's going from 900 to 450. Yeah, fine. So 900 to 450. So where is 450 on this log scale then? So that's 100, 200, 300, 400, 450. So I think it's safe to say that that's something like 2.5. And it's not seconds, it's throws, isn't it? But there we go. It's, that's our time unit here. Our time unit is in throws. Cool. So therefore, lambda is equal to log 2 over 2.5. And that gives us 0.277. Throws to the -1, we might say. Okay, and then we're being asked to show that the number of sides on each die is 4. So triangular die, that's weird, but whatever. So let's remember, what is lambda itself? It's the decay constant. And what is the definition of that? Well, we know it's the probability of a nucleus decaying in the next unit time. And so it's seconds to the -1. In this case, it will be throws to the -1. And so therefore, we can see that the probability of a dice decaying is that. So we can see that it's essentially a quarter. So if we just do 1 divided by that, 1 divided by 0.227277 rather, we end up with 3.6, which is around 4. So in other words, there's a 1 in 4 chance of a nucleus decaying, which means that there must be 4 sides per die in this case. But not an easy question. In fact, it's a very jerk question. So that's classic AQA. Okay, 7.3. We have 2 different sources. One safety measure when using a source in a school lab with a low activity. So school source, don't touch with fingers, use tongs, put in shielded box when not in use, minimize exposure time. Hospital source, however, way more dangerous. So we're talking about your radiotherapy and that kind of thing. So we need lead shield between source and staff, medical staff, we can say. We can say we can use robotics to handle. We can't just use longer tongs because this is way too dangerous for that. What else could we say? Encase source. I've got to be careful here. It is going to be just, this isn't going to be a source that is used as a tracer. It's just going to be a lump, I'd guess, of some isotope. In thick lead, apart from, let's just say hole through which radiation is transmitted at appropriate part of body. 7.4, X-rays are a form of radiation, ionizing radiation. Every 6 months, dentist only takes X-ray images when the person has reported problems. Suggest why. Increased dose of radiation increases chance of damage done to cells, which can cause genetic mutations leading to cancer. We could then say, well, why do we scan at all? Well, it's because scan should be done when benefit of the scan outweighs the risks. Silly question, whatever. All right, multiple choice. In which process is work done by an ideal gas? Okay, so you should remember that if you compress a gas, you're doing work on the gas, because we know that work done on or by a gas is equal to P delta V. There needs to be a change in volume. So therefore, we're talking about expansion. So which of our answers is going to give us that? Doubling the pressure at a constant volume? No, because there needs to be expansion or compression. B, doubling the volume at constant pressure? Yes, because that means that it's expanding. That's correct. Let's just check the other one. C, doubling the absolute temperature at constant volume. Again, constant volume, not the case. D, doubling the pressure at constant temperature. Well, if that's the case, so PV equals nRT. So if that means that temperature is staying constant, then this is staying constant. So therefore, PV is equal to a constant. So therefore, P is inversely proportional to V. So therefore, if we're doubling the pressure, then that means that the volume is going down, it's halving. So that is the opposite. That would be us doing work on the gas, not the other way around. 9, 3 molecules have speeds 2, 4, and 5V. What's the C RMS speed of these molecules? Oh, that's interesting. It's not often we actually have to do this. Interesting. So what we do is that we square them all. So 2 squared plus 4 squared plus 5 squared. And then we divide that by the number that we have. That's 3. And then we do the square root of all of that. And so that's going to be the square root of, what's that? 4 plus 16, so 20, so 45. Is that right? Divided by 3. And so that is the square root of 15. And we got three numbers that are very close. Ooh, I don't actually know that off the top of my head. I probably should. It's 3.87. So our answer is C. That's probably caught quite a few people out, honestly. Okay, that one probably caught a lot of people out, I guess. Okay, initial temperature is 300 Kelvin. The product of pressure and volume is 5,000 joules. Right, so that's equal to nRT or NKT. The gas expands at constant pressure and does 1,660 joules of work. So work done is that. Okay. What is the final temperature of the gas? Okay, so here we have P staying the same, but we still need, that's interesting actually. Let's have a look. So we got PV equals nRT. P is staying constant and an R are constant, so we can say V is proportional to T. Now, does it matter? There is a bit of a shortcut here, I think. Does it matter if we just say that V is 5,000? I don't think it does, because pressure is constant. It's just going to be all relative. So therefore, I think that V1 over V2 is equal to T1 over T2. So we're looking for T2, so let's write it out the other way instead. V2 over V1 equals T2 over T1. So take that over the other side. That's T1 times V2 over V1. So I think that's going to be equal to the initial temperature, 300, times by V2. Now that's the new volume, but because pressure is constant, like we said, and it's just ratios here, we can just say it's going to be 5,000 plus 1,660. It's all relative. So let's go for 6,660 divided by 5,000. Cancel a 0, why not? Actually, we can cancel those zeros too. Ooh. So I think that's going to be 666 times by 3/5. And that gives us basically 400 Kelvin. So I think the answer is B. That was a nifty little shortcut there. 11, we have a capacitor and resistor. They're moved further apart, right? So we have our equation for this. Okay, they're connected though. So they're still connected. So we need to remember this. So still connected. What is staying the same? What is staying the same? V stays the same. Has to be the case. But Q changes because of C changing. Okay, so what's happening? Well, we can see that C is inversely proportional to 1 over D. None of these are changing on the top here. So therefore, if D goes up, separation goes up, capacitance goes down. And we can see that if Q is equal to VC, then that means that if V is staying the same, like we said, C goes down, so does Q. So there we go. Let's have a look at our answers then. So A decrease in potential difference. No, V has to stay the same if they're still connected to the battery. B, a decrease in the charge held. Yes, our answer is B. Let's check the others. C, an increase in the energy stored. No, it's going to be the opposite because energy is equal to half QV equals half CV squared equals half Q squared over C. Which would we be concerned with in this case? Of course, it would be this one here, because V is staying the same but we want to know what's happening to E when C changes. So if C goes down, then so does the energy. And D, of course, we can see that it's a decrease and not an increase in the capacitance. 12, what will increase the efficiency of a transformer? A, increasing the thickness of the ion layers. No, the thinner the layers, the more efficient it is, because that means that eddy currents can't flow as much. B, decreasing the frequency of the AC input voltage. That's an interesting one. I'm going to leave that one for now and come back to it. C, decreasing the diameter of the copper wire. No, if the diameter goes down, then that means the resistance goes up. So that's going to make it less efficient because energy is going to be lost due to more resistance. D, increasing the distance between the primary coil and the secondary coil. No, that's going to do the opposite because the magnetic field wouldn't be as strong in the secondary coil, and so that's not going to be the case. So it has to be B, but let's have a look at that. Decreasing the frequency of the AC input voltage. Interesting. So why is that the case? Well, I'm not sure that's correct. I think they've messed up here. Why do I say that? Well, if you think about it, if we decrease the frequency more and more until it's basically just DC, then it's not going to work. So I would have thought that increasing the frequency of the AC input voltage would increase the efficiency. Yeah, looking at the examiner's report, they've given the reason of increase the time for the change in flux and therefore decrease the eddy currents in the core. I'm not so sure about that one. I mean, yes, we can figure it out, by process of elimination, but that is not a sort of common bit of knowledge that you're supposed to know as part of the course. So again, similar to another question that we had earlier, that's just, you can't do that AQA. You can't just put random stuff that in from like degree or, above level into A-level questions just because you like it. It's ridiculous. 13, signal generator supplies sinusoidal root mean square. Okay, so VRMS is 7 volts. The screen has 8 vertical divisions. Oh, what? Which volts setting will display the tallest complete waveform? Okay, so we know that at peak voltage, the conversion factor is root 2, so 7 times root 2. So that gives us 9.9, so we might as well. Oh, okay, so just below 10, fine. So 9.9 volts. So if it's got 8 divisions, so tallest complete waveform, right? So it needs to be, there's equilibrium in the middle, and then it needs to be like that. And so that means it has to be 10 volts up here, minus 10 volts down here. We need the complete waveform. And so peak to peak, it's not often we talk about peak to peak voltage, but peak to peak is 20 volts, fine, 19.8 volts, but that's the idea, isn't it? So we need it to be about 10. So that means that we need 20, but basically we need it to be at least 10 volts at the top there. I haven't done 4 there. Okay, so 8 times 1.5, that would be, no, it wouldn't, sorry, that would give us 12. That's no good. We need essentially 20, or more than 20. It's not going to be B because that's just going to be 16. So C looks pretty good. So 8 lots of 2.5. And that's just going to give us, that's going to give us 20. And so that's all good. The peaks are just going to be below the top and the bottom, whatever. They're going to be close to clipping, but not quite. So that's going to be C. Of course, if we picked D, then the wave would show up. It's just that it would be a smaller wave on the oscilloscope. 14, what are these 2 crazy waves? Which row shows the frequency of both signals and the phase difference between them? Right, okay. So we want one complete wave, but we haven't got one complete wave. Oh, yes, we do. What am I chatting? So that is, let's go from that point to that point. So 1, 2, 3, 4, 5, 6, 7, 8. So one wave equals 8 divisions. And so that is equal to 8 times 5 equals 40 milliseconds. So that's our time period. So therefore, frequency is going to be 1 divided by that. So 1 divided by 40 times 10 to the minus 3. So it's obviously going to be 25 then, isn't it? So it can't be A, it can't be B. And the phase difference, well, so let's see where they cross equilibrium. They are 3 little divots apart. So that is 0.6 of a division. So phase difference equals 0.6 divisions. Again, times that by 5. And that gives us 3 milliseconds. Okay, so they are 3 milliseconds out. So that's not the phase difference. Sorry, I shouldn't have said that. That's not difference in time. Phase difference, of course, is just a ratio of the bit divided by the lot. We can either use distance and wavelength, but in this case, we're using difference in time and the time period. So it's going to be 3 divided by 40. And we want it in radians, it seems. So therefore, we're going to multiply by 2 pi. The answers are being given in pi. Which makes sense, and so therefore that's just going to be 6 over 40 pi. So I think it's going to be 0.15 then, isn't it? So I think the answer is D. 15, transmission cable, energy, we have a frequency of 50 hertz, which makes sense. Which change gives the largest increase in the efficiency of the electrical energy transfer along the cable? Oh gosh, this is similar to the transformer one. Okay, so A, doubling the transmission voltage, yes. Oh, gives the largest. Ooh. Okay, so V times 2. That's interesting. B, doubling the current. That's not going to be it, is it? Because we know that the higher the current, the more energy lost due to resistance of the cables because of P equals I squared R. Remember, we don't use P equals IV for power lost in cables. It doesn't work. Because that V is not going to be the right V. So it can't be B. C, halving the resistivity of the material of the wires. Isn't that going to have the same effect as A? I don't know. Let's have a think about that. So D, halving the number of wires in the cable. No, that's going to increase resistance, isn't it? Oh, I got it. Of course. So if we know that, actually, we're going to be using this. So we know that if V doubles, then I halves. And so therefore, we can see that, well, if that divides by 2, then the whole power lost divides by 4. So that is our answer there. Not an easy question, though. Very mean. 16. What is the number of circuits completed by the electron in 1 second? So that's frequency for crying out loud, right? So we're going to say BQV is equal. Now we're dealing with frequency here. So we could go with omega squared R, but because we have V as part of the equation for the force, we're going to stick with V's and we'll deal with the whole frequency thing in a minute. So I'm going to say mv squared over R, and one of the V's cancels, fine. And we know that V is equal to omega R. And so therefore, popping that into here, we end up with BQ equals m omega R over R. R's cancel, and we know omega is equal to 2 pi f, and ultimately that's what we're looking for, like we said. So therefore, I'm just going to move, let's write that. So BQ is equal to, I'm going to say 2 pi fm, moving everything else to the other side. And of course, we are talking about an electron, so it should be BE instead of BQ in this case. So F is equal to BE over 2 pi m. There we go. So our answer is D. 17, we have this proton capture. Okay, we're talking about the energy released. Well, that's okay. We're just looking for the difference, aren't we then? So the difference, or the mass defect, is going to be equal to that 13.99. We might end up with a minus. I'm doing this the wrong way around. In fact, yes, I am, but that's okay. I might take so many significant figures. And I'll tell you what, let's say minus plus that. So just mass before, total mass before, take away mass, total mass afterwards. And that gives us 0.0081 U. And looking at our formula sheet, we know that 1 U, when turned into energy, is the equivalent of 931.5 mega electron volts. Am I going crazy? I can't see it on the formula sheet. Oh, there it is. Yeah, I always miss it. It's just right at the end of the constants at the top there. It's just tucked away below atomic mass unit. Cool. So therefore, this is equal to 0.000. So what does that give us? That gives us 7.5 mega electron volts. So it's C. 18, another nuclear themabob. Okay, what is going on? Don't expect it. Okay, I'm going to write it out. Fine. Right. Which statement is not true? A. The lanthanum has the greatest binding energy per nucleon of the 3 nuclides. Okay, so greatest binding energy. So if you think about our graph, and so it looks like this. Okay, so A, lanthanum has the greatest binding energy per nucleon of the 3 nuclides. Okay, well, if you have our graph here, we know what's the isotope that has the highest binding energy per nucleon. That is iron 56. And so it stands to reason, and with a mass of 56, it stands to reason that if bromine 87 is like here or something, then it's going to be closer than the lanthanum, which is going to be over here somewhere. So actually, yes, the bromine is going to have a closer binding energy per nucleon. Yes, I know we don't know the whether it's the correct isotope or normal isotope, but we can infer pretty much that is the case. So no, bromine bromine 87 is closer to iron 56, therefore has higher binding energy per nucleon. Okay, let's just check the others, and if you didn't know that the answer was A, I'm pretty sure we could infer it, do process of elimination. Let's have a look. B, the mass of the uranium is greater than the sum of the masses of that and that and that. Yes, because we know that mass is being turned into energy. That's the whole point of fission, so therefore that is true, so that's not our answer. C, the binding energy of the neutrons released in the reaction is 0. Oh, yes, that's true. I got confused then. I was like, yeah, that's true. Yes, that's true. An individual nucleon doesn't need any energy to separate it from anything else. So yes, no binding energy if they're on their Todd. Finally, D, the binding energy of the U is greater than the binding energy of the lanthanum. Yes, by definition, we're not talking about binding energy per nucleon, just the total binding energy. So we have more nucleons in the uranium, therefore it's going to have a greater binding energy. It's going to require more energy to break it apart into all of its constituent protons and neutrons. Not a super easy question though, that one. 19, go with 5.6 kilowatt hours. It's released when 1 kilogram of wood pellets are burned in a power station. What is the mass lost in burning 1 kilogram of what? What is the mass lost? Is this a trick question? No. I don't understand. We're not turning mass into energy. Are they really expecting us to say that this is a nuclear reaction of some sort? But there's no mass lost. Let's just check. So let's turn this into joules. So 5.6 kilowatt hours. So that's 5,600 watt hours. So if we multiply that by 3,600, we end up with watt seconds. So that's 2.02 times 10 to the 7 watt seconds, which is the same thing as joules, because power is equal to energy divided by time. Therefore, energy is equal to power times time. That is watts times seconds. Okay, so we got that many joules. Are we really expecting to do mc squared? So we're looking for mass. That's going to be E divided by C squared. Guys, this can't be right. Let's just call that 9 times 10 to the 16. Guys, the answer, if we do this, is that many kilograms. And so that gives us the answer C. I am at a loss as to what is happening right now. I'm genuinely freaking out here. Okay, I'm going to forget about that one before I really lose my sanity. Boy. Nuclear radius of an element of nuclear number X is R. Right, so we need to talk about our radius equation. So radius is equal to R0, a to the third, and so we can just say that R is proportional to a to the third, but in this case they've just given us a different letter, that's all. And so R is proportional to x to the third, or rather we don't even need that, to be perfectly honest. So we can say that R1 over R2 is equal to A1 to the third divided by A2 to the third, but actually that just ends up being x to the third divided by y to the third, but I'm going to just combine those as well. And so therefore, if we're looking for this, then just flipping everything on its head, we're just going to end up with R1 times by the reciprocal of this, so it's just going to be y divided by x to the third. We don't need that R. So the answer is D. Question 21. Enjoy the bad microphone quality, guys, because I messed up this question the first time around and I'm currently away from my Rode NT1 mic. So let's have a look at this one. Here we have another planet. We're talking about M is changing, T is changing. And so we want to know how is R changing. And so if it was just T and R, we'd be looking at Kepler's law, Kepler's third law to be precise. But that's for if we're just considering things orbiting the same body, mass isn't changing in the middle, and so therefore we need to be considering the whole shebang. So we're going to go for, as per usual, things that orbit gmm over r squared. I'm going to use a big R for this one, methinks, and that's equal to, we could go with mv squared over r, but the thing is that we're looking at time period, so therefore we're going to say m omega squared r instead. M's cancel. One of the r's goes over there, so we end up with r cubed, and of course this is where we get Kepler's law from when we derive it anyway, so gm over r cubed is equal to 2 pi f squared, but because we're talking about time period, we're going to go with 2 pi over t squared instead. So g is constant, and pi and 2 are constants, so therefore we can say that m over r cubed is proportional to 1 over t squared. And so if we're looking for how r is changing, then we're going to say that r cubed is proportional to, just going to move that up there, so it's just proportional to mt squared. There we go. And so therefore r is proportional to the cube root of mt squared. And so we don't have to make an equation for this because we don't have actual values, it's all relative, so we don't need to go for, you know, m1, m2, r1, r2, and t1, t2. So let's just go with this. What's happening to the mass? The mass is twice that of Earth. The time period is a quarter. But because it's squared, that means that's going to be divided by 16. And so therefore we're looking for the cube root of times 2, so divide by 8, so an eighth. So the cube root of an eighth, and so that ends up being a half. So our answer is C. Not a super easy one though. Asteroid has a mass of 2 times 10 to the 17 kilograms. Escape velocity is 40 meters per second. What is the order of magnitude of the radius of the asteroid? Right, escape velocity is all to do with energy. We can talk about potential as well, but we'll do that in a sec. We can say gmm over r is equal to half mv squared. One of the m's cancels. This is actually big M, not little m. And, well, there we go. We can just rearrange it if we're talking about v's. So if we're looking for r, we can just swap the half and the v squared with the r. So therefore r is, so there we go, swap all of that around. So therefore r is equal to gm over a half v squared. So that's basically 2 gm over v squared. Okay, and so if we're talking about orders of magnitude, then we're talking, this is going to be 40 squared. So that's going to be 1,600. So I'm going to say that's times 10 to the 3. And then g, that's 6.67 times 10 to the minus 11. So I'm going to say that's times 10 to the minus 10. We don't need the times. I'm just writing out for effect. And the mass is times 10 to the 17. Okay, so combining all of these, so we have here 10 and 7, minus 10 and 17. So this just ends up being 7, and then divide by 3. So this ends up just being 4 altogether. So I think the answer is B. 23 diagram. We got equipotentials and all that jazz. Oh, that's annoying. They've done equipotentials as solid lines and gravitational field lines as dashed lines. Convention says it's the other way round, guys, but whatever. Okay, which statement is correct? More work is done from moving from Q to S than moving directly from Q to R. No, it's the same energy, same work, because they are, R and S are on the same potential, same equipotential. So therefore, that's not going to be our answer. Doesn't matter how far away it is, it just matters what potential, what equipotential they're on. No work is done from moving from Q to R. No, that's not true because we are going from one equipotential to another. C, the gravitational field strength is the same at R and S. No. because we can see that the field lines are different. They're closer together, R compared to S. And that makes sense because R is closer to both of these than S. So it's probably going to be D, but let's just check. The work done moving from Q to R and from Q to S is the same. Yes, because Q to S to R. Yeah, because, you know, that's just the opposite to A, isn't it? And so we've already proved that, so that is correct. 24, what is equal to epsilon 0? It's the permittivity, it's not the relative permittivity of a vacuum. The relative permittivity of a vacuum is 1. That's the point. And then we add in epsilon r, 1.3, 1.5, 2 for different dielectrics and all that jazz. So that is not our answer. B, the charge stored on a capacitor consisting... Oh, my days. Okay, fine. We're going to have to write out our equation. So that... we're not going to have relative permittivity because we're just dealing with just vacuum, air, whatever. So therefore, we're going to say epsilon is equal to CD over A. Okay, so what are we told? The charge stored on a capacitor... Oh, great, we're going to have to go one step further. So Q is equal to VC, therefore C is equal to Q over V. And so therefore, popping this in here, I think this is going to be our answer because it's complicated and that's the kind of thing that happens. So we end up with QD over VA. So the charge stored, yes, considering a two parallel plates of 1 meter squared, yes. Separated by 1 meter, yes. When the PD is 1 meter, yes. That is our answer. Let's just check the other ones. The work done when moving a 2 coulomb charge from infinity to the metal sphere. I have no idea. No, I don't. Infinity. I don't know. I mean, it doesn't strike us as the right answer. C, does it? D, the charge on a metal sphere when experiences a force of 1 Newton when the center is placed 1 meter from the center, 1 coulomb of charge. No, because, you know, we're not concerned with forces when it comes to thingies, are we? I don't think so, no, when it comes to permittivity. Why can't it be C? I'm not struggling to understand C. The work done when moving a 2 coulomb charge. I mean, the fact that it's... infinity to... No, that doesn't strike us as right, does it? There we go. They just seem like nonsense. 25, force between 2 point charges is F, magnitude. Okay, so we're going to need F equals K, Q1, Q2 over R squared. Cool. So the magnitude of each charge is doubled. So times 2, and the distance between them is halved. And so that means that R squared altogether goes down by 4. So therefore, that means that the whole thing then multiplies by 4. So it's times 2 times 2 times 4. So it's going to be 16F. So I think our answer is A. Very classic question. But you might be tempted to cancel the 4 on top and the 4 on the bottom, like I almost did. 26, lots of thingies here. Which diagram shows distribution of charge where the electric potential at P and the electric field at P are both 0? Right. So we know that electric field strength is a vector and potential is a scalar, and so we just add them up. It doesn't matter where they are. Let's deal with our electric field strength first, shall we? Or shall we? No, let's deal with potential first, actually, because that'll be easier just to add them up. So let's have a look at A. So we have plus 2Q, minus Q, and minus Q. So potential is fine. But what about E? No, it can't be the field strength because it's a vector. Of course, if we put a charge there, if it was a positive charge, it would be attracted towards the negative charges and repelled from the positive charges. So no, it can't be that. It can't be A. Let's check B. Potential. No, potential is no bueno here because we have plus 4Q altogether, minus 2Q. That doesn't work out. Field strength would, actually, incidentally, because we have the minus Q's pulling in the opposite direction and the plus 2Q's pulling in opposite directions as well. C looks similar, but I don't think this is going to work out. V is good, but E is not going to be good. Again, if we put a positive charge there, it's going to be attracted towards the negative Q's, repelled from the plus 3Q. So it's not going to be that. So I think the answer looks like it's going to be D, but let's just check it out. So potential is good because we have plus 4Q altogether, minus 4Q altogether. That's good. And then the field strength, yes, we have the plus 2Qs pulling in opposite directions and all of the minus Qs cancelling each other out too. Crazy question. 27. We have a specific charge of minus 7.1 times 10 to the 7 coulombs per kilogram. It is held stationary in a vertical electric field. What are the magnitude and direction of the electric field? Right. So if it's a negative charge, which it is, then that means that the field lines have to be going downwards, because field lines show the direction of force on a positive charge. So therefore, we need the force to be going upwards. What about the magnitude of it? Well, we know that the force due to the electric field has to be equal to mg. What's the force due to an electric field? It's EQ, and so that's equal to mg. But we don't have that. But look at this, we do have coulombs per kilogram. So therefore, if we go for Q over M, that is equal to, moving E over the other side, that's G over E. We're looking for E, so I haven't done a great job of rearranging that there. But ultimately, what we end up with is E is equal to G divided by Q over M. So that's 9.81 divided by our specific charge. Don't really care about the minus in this case if we're just looking for the magnitude. So that gives us 1.38 times 10 to the minus 7. So it's going to be A or B, and it's going to be downwards. 28, which particle has the largest magnitude of electrostatic force divided by gravitational force when separated by the same distance? Okay, let's check A first of all. So we're just talking about orders of magnitude. We don't need the actual numbers. And so we're going to say that, well, of course, this is going to be, tell you what, let's start this again. So this is going to be equal to KQ1Q2 over R squared divided by GM over R squared. And of course, the R's cancel. And so therefore, K is staying the same for everything as well. And G is staying the same for everything as well. So actually, FE over FG is proportional to Q1, Q2 over MM. So the product of the charges divided by the product of the masses. Easy peasy. Let's go for A first. So an electron and a positive pion. Oh, flip. I'm not going to convert that into kilograms, am I? I'm going to have to flip it. So a positive pion, we're giving it in mega electron volts. That's the problem. I don't know. It could be that. Positive pion has a rest energy of 139.576 mega electron volts. If you turn that into joules, so times by 1.6 times 10 to the minus 13, we end up with 2.2 times 10 to the minus 11 joules. And then if we were to do E equals mc squared, and so m is equal to E over c squared. So that's 2.2 times 10 to the minus 11 divided by, I'm just going to say 9 times 10 to the 16. It gives us 2.48. That seems very small. Is it that much smaller than a nucleus, a proton? Yes, of course it is. Sorry, of course it's going to be lighter because it's only 2 quarks instead of 3, isn't it? Right, so we have that. We're going to use that for A and C anyway. I'm not sure if it's going to be worth it, but let's have a crack anyway. Okay, so an electron and a positive pion. So that's going to be this value here. That's going to be... the magnitude is just times 10 to the minus 19 in both cases. And then the mass is going to be, well, an electron is times 10 to the minus 31. And then this is times 10 to the minus 28. And so that's going to be on top, that's going to be 10 to the minus 38 divided by 10 to the minus, what's that going to be? 59. And so that's going to be equal to 10 to the 21. Fine. So we got that for A. This is one that I would definitely leave until the end. A helium nucleus, well, that's going to be a charge of 2 times 10 to the minus 19. So again, we can just go 10 to the minus 19. That's fine. Orders of magnitude. And a proton. So again, and then divide that by, well, 4. We don't really care too much about that, but it's going to be divided by, maybe we do. We'll deal with that if we have to. So times 10 to the minus 27 for a proton, or a nucleon rather, and then it's the same for that. So that's going to be 10 to the minus 38 divided by 10 to the minus 54. And so that's going to be 10 to the 16. I'm running out of space here. C, a proton and a positive pion. And so that's going to be 10 to the minus 38 again, divided by 10 to the minus, 55. It's going to be 10 to the 17. And then finally D, proton and electron. So that's going to be 10 to the minus 19 again. So I don't have to write it down every time, but hey, there we go. I'm doing it. So 10 to the minus 27 times by 10 to the minus 31. So that's 10 to the minus 38 divided by 10 to the minus 58. So that's 10 to the 20. Okay, what are we looking for? We're looking for the largest magnitude. So it looks like it's going to be the top one there. So I think the answer is A. That was like pulling teeth, wasn't it? 29. What can be deduced about the radius of a nucleus of gold from the scattering of alpha particles by gold nuclei? What is the radius of a nucleus? Well, we know that it should be less than 10 to the minus 14 meters. Just one of those niche bits of information that you need to know. You shouldn't have to be perfectly honest, but there we go. 30, we have our classic NZ plot. And the nuclide rhodium, I think that's rhodium, 115, is likely to decay. Okay, so where is it on this graph? So, well, I can't see it there. 115. Oh, so it's right at the top. Oh, no, it's not. Sorry. It's there. And 45. So where is it? Is it above the line or is it below the line? Definitely above the line. So it's there. That is going to be your beta decayers. That's where your beta decayers are, around there. Your alpha decayers are sort of up here. There we go. It's just something you need to know yet again. 31, uranium-238 absorbs a neutron. Okay, 31, we have uranium-238 is getting an electron. It's being bombarded by a neutron. And so what does that turn into? It turns into X. And so that's going to be 239 now, but the number of protons stays the same. And that then goes to Y via beta minus decay. So if that's the case, then it ends up being 93 because we're gaining a proton, but the number of nucleons stays the same. And then same again when it comes to Z. So that's going to be 239 yet again and 94. So therefore the number of neutrons is just going to be the mass number take away the number of protons, and that gives us 145. That was nice and easy to almost finish off on, but what do we have here? Oh, this looks like a complicated one to finish off on. So, rock sample, it contains lead-207. When it was formed, the rock contained uranium, but not contained. Okay, so it's decayed into lead-207, so we don't care about this, but I'm going to write it down anyway. Okay, so it decays by a series of steps, of course. The half-life of uranium-235 is 0.71 billion years. There we go, BY for short. The half-lives of the nuclides in the intermediate steps are negligible. The sample of rock now contains 1 atom of lead-207 for every 4 atoms of uranium-235. Right, okay, so first things first, we need to say that N over N0 is going to be 1 to the number of remaining nuclei. Remember that this is undecayed nuclei, so we're talking about the uranium. That's going to be 4 to 5, because if it's 1 to 4, then the whole ratio is 1 to 5, 4 to 5, and so therefore the ratio of uranium atoms now compared to begin with is 4 to 5, and that is equal to E to the minus lambda T. And of course, we know that half-life is equal to log 2 over lambda. So we can replace this. So we can just say lambda is equal to log 2 divided by the half-life. So therefore, we can say that 4/5 is equal to E to the minus T log 2 over the half-life. And heck, we're looking for the time, so I should have rearranged it first, but whatever. So we're going to log both sides. So log 4, I'm just going to say log 0.8 natural log is equal to minus T log 2 divided by 0.7, that's billion years. And so therefore T is equal to minus log 0.8 times by 0.7 divided by log 2. And I get 0.225 billion years, or in other words, 0.23. So the answer looks like it is A. Whew, that was a slog. Not nearly as easy as paper 1. Paper 1 was an absolute flipping walk in the park compared to this one. So I hope you found this helpful. Leave a like in the comment if you did, and don't forget to click the card to take you to the playlist with all of the papers in, including paper 3A as well. So see you next time.